Hello everyone, it's Maria again, and here I have annotated some slides from chapter 6. So here are some review items. What is a substitution reaction? A substitution reaction is when two Lewis bases compete for the same acid. What is a nucleophile? A Lewis base that can use its pair of electrons to displace an atom. What is a leaving group? A Lewis base that is displaced by the nucleophile. Okay, so this is from the book, but it's also similar to Worksheet 6, problem number 4. So up above, you have the Michaelis-Menten equation. V naught is equal to V max times the substrate concentration divided by the Km plus the substrate concentration. So what is the purpose of the Michaelis-Menten equation? It shows the relationship between initial velocity and the substrate concentration for one substrate. Here are some definitions that you should already know by now, and if you don't, go ahead and stop the video and make sure you memorize these. So the Km is the substrate concentration at 1/2 the maximum velocity. The Vmax is the maximum rate of a reaction. At this point, the enzyme is saturated. No matter how much substrate you add, the reaction can't go any faster. V naught is the initial velocity. This is dependent on substrate concentration. If you have a lot of substrate, the initial velocity will be fast. If you have a little bit of substrate, the initial velocity will be slow. Kcat is equal to Vmax divided by the enzyme total concentration. That's what that E with a little t means. Total enzyme concentration. So this is just something to know. So on this graph, we have on the y-axis, we have V naught in micromolar per minute. And on the x-axis, we have substrate concentration in millimolar per minute. So on this corner, we have low substrate concentration, and on this corner, we have high substrate concentration. So as you can tell, there's different things going on in each of those two corners. So Km is half the Vmax, that's right here. But let's look at the low substrate concentration on the left corner. Here you only have a little bit of substrate, so on the x-axis you can see that the Km is greater than the substrate concentration. For example, if your substrate concentration is on this red dot, the Km is greater than your substrate concentration. It looks to be close to 0. So when you look at the Michaelis-Menten equation, in the denominator, where you would normally add the substrate concentration, so you can see what they're talking about up here, it's Km plus the substrate concentration. But if that's close to 0, then it becomes negligible, and they remove it. As a result, you get a straight line because the V naught is linearly dependent on the substrate concentration. So that's this straight line that you see here. The V naught is equal to the V max times the substrate concentration divided by the Km. Notice that they removed the plus substrate concentration here. Okay, so now let's look at the high substrate concentration scenario on the right. Here, you have high substrate concentration. When you start off with a lot of substrate, you can see on the x-axis that the Km is smaller than the substrate concentration. So if you're over here, then your Km is smaller than your substrate concentration. At this point, the Km becomes negligible, and the equation is simplified to V naught is equal to Vmax, and that's what you have here. Here we have a worked example 6.1 from the book, determination of Km. Once again, Km is the substrate concentration at half of the maximum velocity. An enzyme is discovered that catalyzes the chemical reaction. Sad is converted into happy, and vice versa. So sad is the substrate and happy is the product. A team of motivated researchers sets out to study the enzyme, which they call Happy Ace. They find, sorry if you hear, that's my dog. She's scratching. Okay. They find that the KCAT for Happy Ace, or the KCAT is the enzyme turnover number, is 600 per second, and carry out several additional experiments. When the total enzyme concentration is 20 nanomolar and the substrate SAD concentration is 40 micromolar, the reaction velocity, V naught, is 9.6 micromolar per second. So I don't know if you noticed here, but we have nanomolar, and then we have micromolar, and then we have micromolar. That means that we're going to have to convert this nanomolar into micromolar. So up here on the left, I wrote notes for how to do that. Converting from nanomolar to micromolar. Nanomolar is equal to 10 to the negative 9. Micromolar is equal to 10 to the negative 6. Nanomolar is a smaller number than micromolar by 3 orders of magnitude. So you move the decimal by 3 places to the left. 20 nanomolar is equal to 0.020 micromolar. And that's what this is the number you're going to be using for all of your equations down here. So calculate the Km for the substrate SAD. So they gave you a lot of information, and you have to calculate the Km. So the formula we're going to use is, so down here we have the Michaelis-Menten equation. V naught is equal to Vmax times the substrate concentration divided by Km plus the substrate concentration. They gave us the enzyme turnover rate, the total enzyme concentration, the substrate concentration, and V naught. So they didn't really give us these values, they gave us different values. So this is where you use these facts right here. The KCAT, or the enzyme turnover number, is equal to the Vmax divided by total enzyme concentration, where the Vmax is equal to the total enzyme concentration times the enzyme turnover number. So in this equation, all we're going to do is replace this Vmax with these values right here. The total enzyme concentration times the enzyme turnover number. And so you rewrite your equation as it's seen right here. And then you just fill in all the values. So the V naught was 9.6 micromolar per second, is equal to the enzyme turnover number was 600 per second, times the total enzyme concentration, which was 0.020 micromolar, times the substrate concentration, which is 40 micromolar, divided by the Km, which is what we need to find, plus the substrate concentration, which is 40 micromolar. So then you end up with 9.6 micromolar per second is equal to, you multiply everything on top, and it equals 480 micromolar per second, micromolar squared per second. Don't forget to get the correct number of units up here. So you had 2 of those, and that's why it's squared, per second, divided by Km plus 40 micromolar. And then you want to get rid of the denominator here, so you multiply 9.6 micromolar per second by everything that you have in the denominator down here. So then you end up with 9.6 micromolar per second times parentheses Km plus 40 micromolar is equal to 480 micromolar squared per second. So then you can divide by this value, because remember that parentheses here means that you're multiplying. So the opposite of that is division. So you divide by 9.6 and you're left with Km plus 40 micromolar is equal to 480 micromolar squared per second divided by 9.6 micromolar per second. So Km plus 40 micromolar is equal to 50 micromolar. And then you just subtract this 40 micromolar. So you have Km is equal to 50 minus 40 micromolar. And you end up with Km, which is equal to 10 micromolar. And that's what we were supposed to find. And once again, Km is the substrate concentration at half the maximum velocity. Okay, this is another worked example from the book. Example 6-2, determination of substrate concentration. And before we get started, we're going to go over the definitions that you're already supposed to know. So the Km is equal to the substrate concentration at half the maximum velocity. The Vmax is the maximum rate of a reaction. At this point, the enzyme is saturated. No matter how much substrate you add, the reaction can't go any faster. The V0 is the initial velocity. This is dependent on substrate concentration. If you have a lot of substrate, the initial velocity will be faster. If you have a little bit of substrate, the initial velocity will be slower. The Kcat is equal to Vmax divided by the total enzyme concentration. So here we go. In a separate Happy-Ace experiment, using total enzyme concentration is equal to 10 millimolar, the reaction velocity, V0, is measured as 3 micromolar per second. What is the substrate concentration used in this experiment? So, using the same logic as in worked example 6-1, we see that the Vmax for this enzyme concentration is 6 micromolars per second. So they're using some of the same values from the 6-1 example. Note that the V0 is exactly half of the Vmax. So that observation basically gives us our answer. Recall that Km is by definition equal to the substrate concentration at which the V0 is equal to half of the Vmax. Thus, in this example, the substrate concentration must be the same as the Km, or 10 micromolar. However, if you had not made that observation, or if you had different values, then you would use the expression V0 divided by Vmax is equal to the substrate concentration divided by the Km plus the substrate concentration. So that's the same Michaelis-Menten equation, but you just move things around. Okay, what we've seen until now is one substrate, one product, but 2/3 of all enzymatic reactions actually have 2 substrates and 2 products. So an example is hexokinase. You have ATP plus glucose, 2 substrates, and they're turned into ADP plus glucose 6-phosphate, 2 products. A phosphoryl group from the ATP is transferred to glucose, and you end up with ADP and glucose 6-phosphate. Each substrate has its own Km. Okay, we're back. So I'm going to start over because I don't know if it removed that. Okay, in Michaelis-Menten kinetics, they can be used to differentiate between pathways that form a ternary complex and those that don't. So what is a ternary complex? It's the first substrate, when the first substrate binds, and only then can the second substrate bind? For reactions with ternary intermediates, Michaelis-Menten can also be used to distinguish between ordered and random binding of reactants and products. So for A, we have enzyme reaction involving a ternary complex. And then we have ordered and random. So in the ordered, the first substrate binds, and only then can the second substrate bind. So we have the enzyme plus substrate 1 turns into the enzyme and substrate 1 complex. And then the second enzyme comes in, and then you have the ternary complex, enzyme, substrate 1, and substrate 2. And that turns into the free enzyme plus product 1 plus product 2. In the random order, it doesn't matter which substrate binds first. So you have this over here. You have the enzyme, and you can have the enzyme substrate complex with substrate 2, or the enzyme substrate complex with substrate 1. And then both pathways lead to the enzyme to the ternary complex, which is enzyme substrate 1, substrate 2. And the result is the free enzyme plus product 1 plus product 2. In B, you have enzyme reaction in which no ternary complex is formed. Here, the first substrate binds, is converted into product, and is then released. At this point, the second substrate can bind. So you have enzyme plus substrate 1 equals enzyme substrate complex 1. And then you have the enzyme with that little parenthesis or something. I forgot what that's called. With product 1. So that substrate 1 was converted into product 1. And then product 1 is released. But the enzyme was modified, and that's why you see that little thing right there. So then substrate comes in, substrate number 2. And then you have the enzyme substrate number 2 complex. And then that results in the free enzyme, unmodified, plus product number 2. And then you have Cleland nomenclature. So there's just a few rules that you have to know, and then this won't be so difficult. For substrates, you have A, B, C, and D. That's how you... Okay, sorry. That's what happens when you work from home. So the substrates are A, B, C, and D. The products are P, Q, S, and T. When you have 1, it's uni, 2 is bi, 3 is ter, and 4 is quad. The enzyme, if modified, okay, so the enzyme alone is E. If it's modified, then it's F, G, etc. So here we have an ordered bi-bi and a random bi-bi. So if you have a vertical line, that equals binding and dissociation. So here you have A is a substrate, so a substrate is binding. Here you have B is also a substrate, and it's binding. Okay, so then you have P, so P is a product, and the arrow's going outwards, so that means that it's dissociating. And then you have Q is also a product, and the arrow's going outward, so it's dissociating. And then the horizontal line is the progress of the reaction. So here's the progress, and then vertical again is the binding and dissociation. So you have the enzyme by itself. The first reactant or substrate comes in, and then you have the enzyme substrate complex. And then substrate 2 comes in, and you have the enzyme plus substrate 1 and substrate 2, that complex. Then you have the enzyme and PQ, so those are products. So now you have the enzyme and 2 products. Here it was the enzyme substrate complex, now you have the enzyme product complex. And then you have the first product dissociating and the second product dissociating. So for the random bye-bye, again, the horizontal line is the progress of the reaction. You start off with the enzyme by itself, and then you have the first substrate coming in and the second substrate coming in. Over here, second substrate. So this is one reaction pathway on top, and then this is another reaction pathway on the bottom. So there's two possible ways. You can have substrate 1 and then substrate 2, or you can have substrate 2 and then substrate 1. Either way, you'll end up with the enzyme and both substrates, that complex. And those will be turned into the enzyme and both products, P and Q. And then you have two options again in terms of your reaction pathway. So you can release product 1 and then product 2, or product 2 and then product 1. And you're left with a free enzyme. So then there's also something called a ping-pong and Cleland nomenclature. So here, a group is transferred from the first substrate A, right here, to the enzyme, and a transient covalent attachment is created. Now, the enzyme has been modified. Then the enzyme will transfer that group to the second substrate. So you start off with your free enzyme, and substrate A comes in, the first substrate, so you have your enzyme substrate complex. But here the enzyme was modified. If you remember, the free enzyme is E, unmodified enzyme is E, and then when it's modified it's F. If it's modified again, it'll be G. So here it's turned into F. So it's still the enzyme product complex. So enzyme substrate, enzyme product. But because the enzyme was modified, it's now F. So then the first product leaves, and the enzyme is left unmodified. And then, the enzyme is left modified, that's still an F. And then the second product, or the second substrate comes in, and you have the enzyme substrate complex. And that turns into the enzyme product complex. But you're back to the normal enzyme. If you can see that that's an E, whereas before it was the modified enzyme, an F, but it gave that group to substrate B, and now the enzyme is back to normal. And now you have product Q. So product Q is released, and you're left with a free, unmodified enzyme. Michaelis-Menten kinetics can be used to differentiate between pathways that form a ternary complex and those that don't. For reactions with ternary intermediates, Michaelis-Menten can also be used to distinguish between ordered and random binding of reactants and products. Here we have two substrates, and these are their double reciprocal plots. The first substrate concentration is varied, but the second concentration is held constant in both plots. So here, on the y-axis, we have 1 over V naught in 1 over micromolar per minute. And on the x-axis, we have 1 over the substrate concentration in 1 over millimolar. So remember that we have the double reciprocal plots in order to get these straight lines. So here, the intersecting lines equal the ternary complex right here. So when you see this, you know that a ternary complex was formed. When you see parallel lines, it means that no ternary complex is formed. Okay, enzymes can be inhibited either reversibly or irreversibly. So reversible inhibition, 1. Competitive inhibition. the inhibitor binds the active site and prevents the substrate from binding. The alpha Km is called the apparent Km, and it is the Km that you see when the inhibitor is present. If you add more substrate, then you reduce the chance that the enzyme will bind the inhibitor. The substrate concentration will increase to achieve the same Vmax. And here you have your equation. V naught is equal to Vmax times the substrate concentration divided by the alpha Km plus the substrate concentration. So the second type of reversible inhibition is uncompetitive inhibition. Inhibitors bind to the enzyme substrate complex at another site. The measured Vmax will be lowered. The apparent Km is also lowered. And here's the equation. V naught plus the Vmax times the substrate concentration divided by the Km plus the alpha prime, and then substrate concentration. And then number 3, you have mixed inhibitors. So these can bind to the enzyme or to the enzyme substrate complex, but they don't bind the active site. Km and Vmax are affected. The inhibitor will result in some of the enzymes, enzyme concentration, inactive, and the Vmax depends on the enzyme concentration. The Km will go up or down depending on what the inhibitor binds to, either the enzyme or the enzyme substrate complex. And the equation is V naught is equal to Vmax times the substrate concentration divided by alpha Km plus alpha prime substrate concentration. The effects of reversible inhibitors on apparent Vmax. So inhibitor type, if you don't have an inhibitor, the apparent Vmax is the Vmax, and the apparent Km is a Km. But with a competitive inhibitor, you have the normal Vmax, and then alpha Km. And remember, alpha is apparent, and you just multiply it by that value. Uncompetitive, you have a Vmax divided by alpha prime. And for the apparent Km, you have Km divided by alpha prime. For the mixed, you have Vmax divided by alpha prime, and then you have alpha Km divided by alpha prime. Here's an example, 6-3. Effect of inhibitor on Km. The researchers working on happy ACE discover that the compound stress is a potent competitive inhibitor of happy ACE. Addition of 1 nanomolar of stress increases the measured Km for SAD by a factor of 2. What are the values for alpha and alpha prime under these conditions? So remember that the Km is the concentration of substrate at half the maximum velocity. So if the Km is increased, it means you need a higher substrate concentration to reach the same maximum velocity. So the solution, recall that the apparent Km, actually let's review the competitive inhibition. The inhibitor binds the active site and prevents the substrate from binding. The alpha Km is called the apparent Km, and it is the Km that you see when the inhibitor is present. If you add more substrate, then you will reduce the chance that the enzyme will bind to the inhibitor. Okay. So V naught is equal to Vmax times substrate concentration divided by the alpha Km plus the substrate concentration. So recall that the apparent Km The Km measured in the presence of a competitive inhibitor is defined as alpha Km. Because Km for SAD increases by a factor of 2 in the presence of 1 nanomolar of stress, the value of alpha must be 2. The value of alpha prime for a competitive inhibitor is 1 by definition. Sorry about that. Okay, so they will destroy a functional group. Oh wait, let's start over. So irreversible inhibition. Irreversible inhibitors do one of three things. They bind covalently to a functional group that is essential for the enzyme, or they destroy a functional group that is essential for the enzyme, or they form a highly stable, non-covalent interaction. The result is that the enzyme will be inactivated. So with irreversible inhibition, the result is that the enzyme will be inactivated, and you can inactivate the enzyme by one of these three mechanisms. You'll also have suicide inactivators, mechanism-based inactivators. This is a special class of irreversible inhibitors that follow the first few steps in the enzymatic reaction until they combine irreversibly with the enzyme. Drugs made using this mechanism have few side effects. Okay, so these are some extra notes from your book, nucleophiles and electrophiles. If you need practice with that, go ahead and read that. And then make sure that you've learned all of your amino acid structures and your functional groups moving forward.